Hello, sorry I couldn't be there today. Sorry, life is just not aligning this week for me. My little one was sick. So, giving her the day off, it's my turn to take her during her day off. Get through this lesson. Not too bad, very similar to the last lesson, but instead of looking at exponential functions, we're looking at logarithmic functions, and which are very related. So first let's figure out the relations between an exponential and logarithmic expression and function, and then we'll go from there. So if you look at this relationship right here between an exponential form the relation between the 2, the 3, and the 8, meaning 2 to the third power equals 8, we're going to write that the relationship between those three numbers are going to be the exact same thing, but in a new form. New form is going to look something like this, where we have this notation of log, log, and sub value, kind of like a y sub 1. We're going to put the 2, and then on the same line with the log is going to be 8, and that is equal to 3. The relationship of 2 to the third equals 8 is the exact same thing, 2 to the third is 8, exact same relationship over here. But if you see in this over here, in the exponential form, the value of the power 2 to the third equals 8 is what we get as a result, 2 to the third equals 8, the calculation. Here, the calculation of log base 2 of 8 gives us 3. So now this expression, this logarithmic expression, rather than an exponential expression, gives us a result that is the exponent, right? So 3 is the exponent, and in exponential form, the exponent is part of the calculation. In the logarithmic form, it is our answer. So that's the structure of a logarithm, and we're going to be getting into the calculations, characteristics, and function characteristics of a logarithm. So if we take this log base 2 of 8 and we make it a function, log base a of x, with f of x being the output. First, how do we read it? The way we read it right here is log base a of x, or you could cut out the base and just say log a of x. And a is always going to be greater than 0. That's our base, just like in exponential form. The output is going to be the exponent of the relation between the numbers. We have two specific special logarithms. First one is when our base is 10, so like 10 to the first, 10 to the second, 10 to the third, and so on. Instead of writing log base 10 of x, we would just write log x. So if you don't see a base there, that base is always going to be 10. We'll look at some more properties of the functions as we move forward, but let's just work on some basics here in terms of making sure we're comfortable with the relationship between exponential and logarithmic form. So for example 1 here, you'll have a few problems in your assignment today where you're just rewriting the logarithmic equation exponential equation as an exponential equation and vice versa. So for letter A, 3 is our base, 4 is our exponent, and that is equal to 81. Over here, our base is 2, the exponent is 5, 2 to the 5th, and that is equal to that term there, 32. I am going to back up a bit and indicate that over here, 8 is our value of the power. Over here, we aren't going to call it a value. We're going to call it the argument. So x is going to be called the argument. And then our output is the value. So it kind of can get confusing because here we're calling this the value, but here we're calling it the argument. And they're inverse functions of each other. So when we say, if we look at terms like input, output, x and y, independent variable versus dependent variable, that's the same relationship of the term argument to value. So when we say this is the argument, other math teachers call it the of, and that comes from this lingo right here. But formally we can call that the argument. And then we know the argument is equal to the base to the value of the logarithm. 2 to the third gives us the argument. So coming back to example 2 here, if we want to write these exponential equations in log form, first write the notation of log. I always like to, not always, but usually like to write with like a cursive L instead of a lowercase cursive L, so it doesn't look like a 1. You know, way down here it kind of looks like a 1. Don't have to do that though. The base is 8. The argument is going to be 64 because that's the value of the power. And then our exponent goes after that. Same here, just a little more challenging. Log base 3. The argument is 127. And that is equal to the exponent, which is negative 3. All right, let's start calculating some function values. And calculating function values, we'll have to start thinking about the thinking for doing the calculation. So first off, let's just treat this just like a function, like it is. Plug in 4 for x as it asks for, and then I'm going to write log base 16 of 4. Notice I wrote the cursive L again. Don't have to do that, but I like doing that. And so how do we calculate this? Well, we're thinking about this number to this exponent gives us 4. So you're asking 16 to what exponent gives us the argument 4. So 16, if I take it to the first, it would be 16. 16 squared is like 256. So notice I said 16 in the first, 16 in the second, the exponent 1, 2. That's making it, 1 makes it the same and 2 makes it bigger. We want to make it smaller, so we want to go to fractions. Well, we know that we'd square root 16 to get 4. Well, square root as an exponent is 1/2. We can talk about more about fractional exponents. So the output, f of 4, is equal to the exponent that makes 16 4, which would be 1/2. So f of 4 equals 1/2. Here, again, we're just going to plug in f of 10 equals log 10. Notice I can put parentheses there as well. Or if we have log 10, the bases are in, that's a base of 10 right there. So to calculate this, I ask myself the question, 10 to what exponent gives us 10? Notice I said exponent, not power, because the whole term is called a power. I don't want to get confused with that, particularly when we're just starting out working on logarithms. And I know you did see this last year, but nonetheless, it's second time revisiting, which is fine. Again, takes multiple exposures in math to really get a deeper understanding of what we're looking at. So 10 to what exponent would give you 10? I would take 10 to the first, and that would give us 10. So f of 10 equals 1, because again, the whole logarithm is equal to the exponent. Let's write this last one a little more challenging. F of a to the negative third equals log base a of a to the negative third. So now we're asking ourselves, a to what exponent would give us a to the negative third? And if you can't figure out the other ones, I think we're a little easier to figure out in our head, but now it's not as obvious. So a to what exponent? Remember this I'm putting like a line, like, I want to fill in the blank there. I could put a variable there, I guess. You put x or y or whatever. A to what exponent? A to what exponent equals our argument, which is a to the negative third. So it's a to the negative third. So you simply ask yourself, what would I fill in that blank to satisfy this equation? And it's obviously negative 3. And remember, that's our output of the function. So f of a to the negative third equals negative 3. So moving on to the next page here, We are looking at just evaluating some logarithms with your calculator. It's pretty straightforward. In your Desmos calculator, you just type in log 4.5. But remember, this is a base of 10, so if you plug it in, it will give you the answer. And if it gives like a sub base, like it may go like this, and then give like boxes like that, you're just going to fill it in. You just fill in a 10 for that base box in 4.5. I can't show that on my iPad, but if you did that, you get the answer. You also think about this as a base of 10. This equals, like if we put x, 10 to the x equals 4.5. And think about it, 10 to the first. It's kind of important to go through this lesson. We'll look more at this. But 10 to the 0 equals 1. 10 to the first equals 10. 10 to the second equals 100. So we look at if we have 4.5. 4.5 is somewhere between 1 and 10. So therefore the exponent is going to be somewhere between 0 and 1. I don't remember what it is offhand. I think it's like 0.67 or something like that. I don't have it in front of me. I don't have a log calculator, so you can just easily plug it in and see what it is. And also the completed notes will be posted, which will have the answer. Log 86, so that's saying 10 to what power gives a, or 10 to what exponent gives us 86. Well, 86 is somewhere between 10 and 100, so this is somewhere between 1 and 2. And again, like I said, it's like 1.8, 1.9, somewhere in there. And it's actually not directly proportional. These are dealing with exponents, so 86 is, 86 is, much closer to 100, so you'd expect it to be much closer to 2 than 1, but it's not directly proportional. But yeah, it's going to be somewhere in like the 1.8, 1.9 region. Log -5, an interesting case. 10 to what exponent gives us -5? Well, that's not possible. You can't take a positive integer or positive real number to some exponent and get a negative, so that's undefined. All right, let's look at some properties here. A in general. A to what exponent will give us 1? We know that we take something to the 0 power to get out 1. A to what exponent would give us a? That would be 1. A to the first gives us a. And then a to what power gives us a to the x. It's exactly the same as what we did before. A to what power would give us a to the x. I would insert that blank. This blank is this blank right here, right? A to this power equals a to the x. A to this power equals a to the x. What would I insert into that blank to make these two equal? I would insert x. This will make a lot. That expression, I don't think it's too difficult to understand. We'll talk more about that, and we're going to be working a lot with that, where we have an argument that, like a to the x, has an exponent. We're going to work on some properties of that as we move forward. Next, this is kind of an interesting one. A to the exponent log a of x equals what? And this kind of gets us into the idea of the relationship between exponential equations, or exponential equations and logarithmic equations, and being able to go back and forth. So in this case, we're actually in an exponential equation. Even though we have a logarithm here, we're in an exponential equation. We have a base, we have an exponent equals some value. So I'm thinking about this as an exponential equation. And we just have a general rule, like if you're in exponential form and you can't solve, or you don't know what the answer is, put it into logarithmic form and see if that helps you. And vice versa, if you're in log form and it's not solved for the variable, or you're trying to solve for the variable, put it into exponent form. So let's go and do that. Let's look at number 4, and let's try to put this into logarithmic form. So we first write log, and then our base goes the sub-value. Our base is a. And keep in mind the value of the exponential equation is the argument for the logarithm. A to the exponent equals the argument. A to this exponent equals the argument being in logarithm form. And I'm going to set it equal to the exponent, right? Log base a of the blank, that goes in the argument, equals our exponent. So I'm just literally going to write out our exponent. Log base a of x. Now I ask myself, what would I insert into this blank in order to get these two equations, or these two expressions equivalent? I would have to insert x. So this is not going to come up often, but what we see is if we have a base of a, the exponent is a logarithm, and the base of the logarithm is the same as this base, then all of this will simplify to be the argument of the logarithm. I'll say that again. A is the base. The exponent is log base a of x. The base of this logarithm, a, if that is the same as this base, then the whole expression will equal the argument of the logarithm. Last one, if log base a of x is equal to log base a of y, then I think it's quite intuitive that x equals y. You can only have one argument that would be equal if the logarithmic expressions are equal. Another way you can think about it is like quote-unquote canceling out the log base a. All right, now we're going to get into what we talked about in the last section, e, or the natural base e, which was, again, 2.718281828. If you just remember it's like 2.7, that's fine. We'll uncover where that base comes from, just like where does pi come from. But those are naturally occurring numbers in our universe. So we then use it, it comes up quite often, just like 10 does. So we have this special notation in logarithmic form, just like we have the variable, or the constant e, that letter representing that constant in general. And now in logarithmic form, whenever you see log base e of x, we are going to write it like this, where it's spelled out, instead of log with a sub e, this is just going to be represented as ln, but we're not going to read it as ln of x the way we read it as natural log of x, not ln of x, natural log x for short, the natural log of x, or natural log x. And then we have two special notations, natural log x and log x, with those special bases of 10 and e, ones that come up often. Okay, so now that we've kind of looked at some properties, did some basic calculations, let's look at what a graph of a logarithm looks like. So let me reiterate. Let's say if I have a to the x equals y, that's an exponential equation. What we're going to uncover here is that the end game is that logarithmic functions are inverses of exponential functions. If we go back to our first unit, inverse functions of each other are functions in which the input and outputs are just interchange. So if I have like y equals 2x plus 4, we just interchange the x and the y. X equals 2y plus 4. So let's take the equation a to the x equals y. That's solved obviously for the variable y. And let's put that into logarithmic form and let's see what happens. Log base a is our base, and then we have y here equals x. Log base a, exponent goes by itself on the right hand side, y becomes the argument of the logarithm. Well, if you look here, we want where our argument is the input of the logarithm equal to y. And so here is an exponential equation where our input is the exponent, or output is the value of the power, and the logarithmic form of this is right here, but we don't want that to be the output, we want that to be the input. Well, the way we did that was interchange the x and y. So this shows us by definition that logarithms are inverses of exponentials. So that being said, let's keep that in mind when we are graphing. So if we think back to last section when we were graphing exponential functions. We had our exponent. We chose our exponent, -2, -1, 0, 1, and 2. And we chose those as exponents, and we did like 2 to the negative second, 2 to the negative first, 2 to the 0, 2 to the first, 2 to the second. It was very easy, relatively easy to get those outputs. Well, now that exponent is the output, and the 2 to the second equals 4. That 4 is now our input. So my suggestion for a logarithm to uncover what's going on, what the graph will look like and its characteristics, the exponent is the output. So we're going to pick the output and then figure out the input that gives us, or I'm sorry, pick the exponent, the output, and then do that calculation. Take the base to the exponent, and that will give us the input. So once again, -2 is going in for all this, so 2 to the -2 gives us x, and then we'll fill this in. So 2 to the -2, that would flip it 1 over 2 squared, which is 1/4. So 1/4. And then 2 to the negative first is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 to the second is 4. And if you look here, this is the exact same input-output table, just x's and y's interchanged as we had within our exponential functions. So let's go ahead and graph these. If I have 1/4 -2, that'd be somewhere around there, right? 1/4 for x, -2 for y. 1/2, -1, 1, 0, 2, 1, 4, 2, and our graph overall will look like this. And note this is supposed to be going straight down. And we see we have very similar characteristics. If you turn that on its side, let's see if I can make that happen. It's kind of, if you look, looks just like a exponential function. Now, of course, that looks like a exponential decay, not growth. This is growth for a logarithm. That's okay. Helps just to see the relation. So basically, it's been inverted to the x-axis rather than the y-axis. And we talk more about why when I just simply rotate it 90 degrees, it looks like an exponential decay, where this is logarithmic growth. Don't worry about that. Okay, so domain. Note we will have, just like we had a horizontal asymptote for exponential functions, we have a vertical asymptote for logarithmic functions, because our input is the value, and you can't take a positive real number to an exponent and get out a negative number. Therefore, our inputs of logarithms are restricted to 0 to infinity. Our range goes all the way from -infinity to positive. Our x-intercept is 1, 0, and that's going to be our key point. Rather than in exponential functions, it was y-intercept. In this case, we have no y-intercepts. The function is increasing as we move left to right. None on horizontal asymptotes, but now our vertical asymptote is x equals 0. That's why we had all of these in here for the exponential functions, because some of them apply to exponential functions and some of them apply to logarithmic functions. Some of them don't apply for both. So our key characteristic of a graph sketching is going to be a key point of 1, 0, vertical asymptote, and then this is our general behavior. And just like an exponential function, doesn't matter if your base is 2 or e or 4, you basically have the same structure. So natural log is saying our base is e, but it's still going to have, provided that base is greater than 1. If it's less than 1, we'll come across examples like that perhaps, and we'll talk about that. That'll be for a later date. We're using this as our base, and we're going to do Spider-Man rolls all the same. So I have a +1, which moves it to the left, and then down 2. So I'm going to take my key point of 1, 0, and I am going to move it to the left 1 and down 2. And that's going to give me, this is now my key point. And it also took, since we shifted to the left, it also shifted our asymptote to the left. We can talk more about that mathematically, why that happens. And then we are going to sketch this, and I may not sketch at it completely accurately. We'll see what happens with the calculations as far as our x-intercept. But now because we have the shift, we do have an x-intercept and a y-intercept. So coming over here, domain, we're just going to look at the graph and go from left to right. What are our inputs that give us outputs? And that goes -1 to infinity. So our domain is -1 to infinity. Range is still all the way from down to up, so all real numbers, -infinity to +infinity. X-intercept, we'll come back to that. Y-intercept, pretty obvious, 0, -2. We know it's 100% certain on that because that's based on the transformations. It is still increasing. There is no horizontal asymptote. And now our vertical asymptote is x equals -1. So now how can we figure out what the x-intercept is? Well, let's just use what we know about the x-intercept. We know the x-intercept, the output is 0. So I'm just going to plug that in and see what we have. So I have 0 equals natural log of x plus 1 minus 2. And I look at that and I go, okay, I want to solve for x. So if I want to solve for x, let's use a little crutch here. Don't write this. Let's say I want to find what x is in this equation. Well, I'm going to have to square root. Sorry about that ugly 0. So before I square root, I have to get that x squared term all by itself. So in general, we have this rule that if x is within a term, like x was within the x squared term, we had to solve for the x squared term. I apologize, it's not the best example of it. But it's demonstrating that if x is in some complicated term, you have to solve for that term first. And that's what we see here. X is in this logarithmic term. We have to solve for the logarithmic term first before we can solve for x. So to get this by itself, I'd add over the 2. And I'm just going to rewrite the natural log on the left-hand side, a little easier on the eyes in my opinion. I added 2 to 0, and that gave us 2. And what I said before was, if we're in logarithmic form and we are solve for the variable, a really easy way to do that is put it into exponential form. It could work for us. Most of the time it does. And vice versa. If we're in exponential form and solve for the variable, we put it in logarithmic form. So let's just try that. Let's put this logarithmic equation into exponential form. Well, what is our base here? Remember this notation, ln. That's not how we say it, but that's how it's written. Natural log of x plus 1 equals 2. Natural log means log base e, which means our base, even though this is a shorthand notation, means that there's a base of e here. And the structure of the logarithm, whether it's at log base 2 or natural log, is exactly the same. E to this exponent equals x plus 1. So let's literally write that out. E is our base to the exponent of 2 equals the argument, which is x plus 1. And now we've uncovered that we can now easily solve for x by subtracting 1 over. So if I subtract over 1, that would be e squared minus 1. And that is our x-intercept. So we come up here and you just write e squared, in exact form is fine, minus 1, comma 0. E is 2.7, square is about 6.8, 6.9, 7.1, somewhere in there. Minus 1 gives us about 5.8, 5.9. If you look here, I went up too quickly, probably more like this. But in any case, graph is fine as far as a sketch. Okay, do the best you can on your homework and assignment. I'll see you on Monday.